Hello everyone, my name is Anvesh. Today I am going to explain you about the practical Byzantine fault tolerance. What are the faults which are occurred in the practical Byzantine fault tolerance, and we'll discuss the algorithm. Byzantine fault tolerance in a distributed system. Here we need to know about the two important topics. What are the Byzantine faults and what is the Byzantine generals problem. The main object of Byzantine fault tolerance is to able to defend against failures. What are the failures? Failures like stopping in between the process and crashing is also considered as failures, and by processing incorrect request. It's also one of the type of the failures, corrupting their local states. These all are the different types of failures which occur in the Byzantine fault tolerance. First, we need to know about the Byzantine faults and the Byzantine generals problems, as I mentioned here. And coming to the Byzantine faults, malicious attacks. What are these attacks? Due to the increase in the uh, growing technology, these attacks were also increasing. Software errors, as we all know, what is meant by the software errors, and producing incorrect and inconsistent outputs. We all know what is the inconsistent output means. So we know what's the answer is, but we will get the some other different type of answer. Hardware failures and network disconnection. These are all comes under the Byzantine failures. Now we are going to discuss about the Byzantine generals problem. Byzantine faults is an incorrect operation that occurred in the distributing system. Omission failure. What is meant by omission failure? Failing to respond to a request or not receiving a request at all. This all comes under the omission failure. What is meant by execution failure or lying? A failure due to sending incorrect data or corrupting the local state. These all comes under the execution failure. And coming to the Byzantine generals problem is an illustrated example of Byzantine faults. What is meant by it? Suppose a group of army people want to destroy the enemy city. In order to succeed, there must be a common plan among all the military people or else all the army people in the group. Here the communication is only by passing the messages. In order to succeed, they must be facing two problems. One is complication and the another one is the challenge. What is meant by complication? There will be a traitors who send out conflicting messages to create confusion among the army people, like who don't want to win the battle, or else who don't want to win their enemy troops, who don't want to win their own army people. And what is meant by challenge? In order to overcome this complication is itself a challenge. We need to find an algorithm that ensures the armies to come to an agreement and attack at the same time. And we will see the algorithm in the coming slides. Real world relationships. What is meant by it? We just consider the real world ongoing things with this example. Generals means the command head, group of military people which is leading by the head of the group is called generals. Generals here we describe as processors. Traitors. Who is the traitors? Faulty processes or faulty system. Their faulty army people or faulty people. Messengers. It is the only process where we can communicate with each other. What is meant by Byzantine's problem scenario? As we discussed, suppose a group of people want to attack an enemy city, which they already plan to attack. One of the general, as the pre-planned, one of the general will issue the order attack or retreat. One or several of the generals may be the traitors, To win the battle, all the loyal generals must attack at the same time. Traitors will be trying to fool the loyal generals by sending the wrong messages, not at all coming for them attack at the same time. In order to stop the traitors' malicious plans, all generals exchange message directly with each other. Like here we see, few generals want to attack, whereas few want to wait. That means retreat. It will create a very big problem because traitors will attempt to fool the loyal generals. As I said before, traitors will attempt the fool to make the fool the loyal generals. To stop the traitors' malicious plan, all generals exchange message directly with each other. Like we will see the further steps in the coming slides. The Byzantine generals problem. A commanding general must send an order to his N-1 lieutenants generals such that all loyal lieutenants obey the same order. That means a group of the head, who is known as the commander. If at all he is going to be the loyal, then all the others loyal generals should obey his orders. If the commanding general is loyal, like in the next case, if the commanding general is loyal, then every loyal lieutenant obeys the order he sends. That's what we are discussing. If at all the commanding general is loyal, then all the loyal generals must and should obey his orders. Like if at all he said attack, then everyone should attack. He said retreat, then everyone should retreat. If at all of them are loyal generals. What is the problem here? How to replicator units reach agreement on a non-replicated values in the presence of malicious faults. Here what is the malicious faults? The traitors who send the wrong message. Those are called malicious faults. Simple voting algorithm cannot handle the malicious faults. It's very difficult to handle the malicious faults by using the simple voting algorithms. Impossibility to reach agreement on censor. Here we use voting algorithm. It's a voting algorithm which uses median values. C sends two different values to A and B. Computer C sends two different values to computer A and computer B. Computer C sends value 9 to computer A and value 12 to computer B. Assumes median and computer A decides its value as 10 and the computer B decides its value as 11. Due to C malicious behavior causes A and B to work with inconsistent values. So it cannot be go very easily because due to the C malicious behavior, A and B gets confused and they cannot go and attack the enemy troops with the confidently. What is the solution? There must be at least 3 M+1 processes to deal with the M faults. Why only 3 M+1? You have a doubt. Why only 3 M+1? Because if at all there are only 4 faults, we cannot 4 faults. That means 4 traitors. We cannot directly consider those 4 traitors or else those 4 are loyal generals. In order to make sure, in order to confirm who are traitors and who are loyal generals, we need at least 3 M+1 processes. That means we need total, if suppose M is equal to 4, 4 faulty traitors are there, then we need at least 13, 3 M+1, that is going to be 13 processes to decide there are only 4 faults in their own troop. There must be at least 2 M+1 communication paths. In order to find out who is the loyal or else who is the traitor, they must be exchanging the messages in the group. In order to exchange the messages, there must be at least 2 M+1 communication paths. Until and unless you don't have 2m plus 1 communication paths, it's become very difficult to find out how many faults are there in their own group. M plus 1 rounds of messages must be exchanged. That means if at all there are only 4 people who are false, then there must be at least 5 rounds of messages must be exchanged, because we cannot identify who is loyal and who is traitors. Coming to the next slide, practical Byzantine fault tolerance. Due to the growing technology, malicious attacks and software errors are increasingly common. Due to the growing reliance of industry and government online information, which also increases the cyber crimes by putting fraud mails, and these all are considered under the malicious attacks. Since malicious attacks and software errors can cause faulty nodes, Byzantine fault tolerant algorithms are increasingly important. The algorithm. If, uh, Now we are going to discuss about the algorithm, uh, which will be like 5 to 6 slides. We will go very detailed about the algorithm, and I will explain you about how it works and how it find out the traitors or loyal generals. Here we need basic setup is that a view is a configuration of replicas which consists of a primary and the backups. Backups is nothing but the prepare, and commit. These three comes under the backups, and which they require as we discussed in the earlier slides. 3m plus 1 is the minimum requirement of finding the m faulty traitors. So here also the same. Each replica is deterministic and starts with the same initial state. The state of each replica includes the state of the service, a message log of accepted messages, and the view number. Here basically the algorithm works based upon 4 different conditions. First one is that a client sends a request to invoke a service operation to the primary. The the 4 conditions which I am going to say, which I am going to tell you about, will be discussed in the next coming slides. First condition is that a client sends a request to invoke a service operation to the primary, and the primary multiclassed the request to the backups, that is prepare, and commits. These 3 comes under the backups. Replicas execute the request and send a reply to the client. As we discussed in the first point in the present slide, replicas will execute the request and send the reply to the client. And the client waits for at least m plus 1 replies from different replicas with the same result. This is the result of this operation. We will see the first client step. Here you can see a client sends a request to invoke a service operation to the primary. First he initially sends his request message to invoke a service operation. Here, O is the requested operation, T is the timestamp, C is the client, and sigma is the signature. A client C requests the execution of operation O by sending a request message to its primary. That means it will, the highlighted part in the diagram shows the C sending the request to its client. Client sends the request of the execution of its operation by sending the request message to backup files. Timestamp T is used to ensure exactly one semantics for the execution of client requests. For example, timestamp could be the value of the client's local time. That means whatever the time which is saved in the client's sends the processes, that is the time taken here as the timestamp, and could be the value of the client's local clock when a request is issued. And primary multiclass the request to the backups. That means it will undergo pre-prepare, prepare and commit. Here we will discuss about pre-prepare, prepare and commit in the following slides. But here in the highlighted of the diagram shows pre-prepared, prepare and commit. In the following three ways how the those three all together called as three-phase protocol. And after the backup after the backups completed, it will send its response to the commit. As we see here, replicas execute the request and send a reply to the client. In the highlighted part we can see that replicas is sending the request message to the whatever requested by the client to itself. The client waits for at least m plus 1 replies from different replicas. We have discussed it in the 14th or 15th slide, I guess. The same thing was mentioned here because client want to make sure whether the reply got from the previous replies from the different replicas, whether they are same or not. Three-phase protocol. In a what is meant by three-phase protocol? The pre-prepare and the prepare and the commit. All these three together called three-phase protocol. In a pre-prepare phase, the primary assigns a sequence number n to its request. That means client initially first of all, when the client asks for the request, then it sends to the pre-prepare message. It sends to the pre-prepare phase. The primary assigns a sequence number to its request, and it multicasts a pre-prepare message with m piggyback to all its backups, and it has in the form of pre-prepare v comma n comma d comma and m, and backup accepts the pre-prepared message provided the signature in the request and the pre-prepared message are correct. It is in the same order of same view. It will not accept the pre-prepared message for the view v and n containing different digest. That means it should be in the same view and in the same sequence number. If at all the sequence number is different from the view number, then it will not be accepted in the next phase, that is prepare phase. It will be not accepted in the pre-prepared message for view v and n consisting the different digest. Sequence number in the pre-prepared message is between a lower water, that means small h to the capital H. It should be in between the small h to the capital H. Coming to the prepare phase. If backup accepts pre-prepared message, then it automatically multicasts all its pre-prepared message to the P, accepted by if it is also in the same signature is correct, message signature is in the same order, and it is in the same view. And in the previous slide, the sequence number in the pre-prepared message is also in the same minus small h to capital H. Here also the sequence number should be in the same order, that is small h to the capital H. And prepared m comma v comma n comma I is true. That means prepared message, prepared same view number, prepared sequence number, and I, these all are in true. Then it automatically requested its message to the next phase, that is commit phase. And pre-prepare for m in v minus 2f matches prepares with the same v comma n comma d. If prepared becomes true, multicast commit message and enters commit phase. This particular slide discriminates with the small difference between the pre-prepare and the prepare phases. If pre-prepared m comma v comma n comma I is true, then pre-prepared m dash comma v comma n comma j is false. That means m is the message requested by the client and v is the view number, n is the sequence number. If these all are true, then it automatically sends it to the next phase. But m dash means there must be some faulty. If m is good, then m dash must be bad. If m dash is some faulty, non-faulty, and such that d of m dash does not equal to d of m. That is, ensures request in the same view and the total orders. Three-phase protocol. Now coming to the commit phase. Accepted by backup if message signature is correct. That means the m value is correct, and in the same view, this is v. And if m is in the same order and the v is also in the same order, then n is also in the same order, then it automatically sends its reply message to its client. That's what I mentioned here. Committed m comma v comma n is true. If prepared m comma v comma n is true for all I, in some set of f plus 1 non-faulty replicas, this particular algorithm also provides safety and the liveness. If the algorithm provides safety because every faulty replicas will not be enter into the commit stage. So it's all faulty replicas and non-faulty replicas agree on the same sequence number of requests that commit locally. That means it shows only the non-faulty processes will enter into the critical section. And to provide liveness, replicas must change view if they are unable to execute a request. To provide liveness, replicas must move to a new view if they are unable to execute a request. That means it should change its own view number. But it is important to maximize the period of time when at least 2m plus 1 non-faulty replicas are in the same view. That means if at all there are some faulty replicas, then it should not change its the view number. Coming to the next slide, optimizations. We use a few optimizations in order to reduce the cost of communication. Like the first avoids sending most large replies. That means it will not send up to a particular limit. It will not send any replies to all the messages. The client request designates a replica to send the result. Only a designated request only it will send the result. And cryptography. Digital signatures used only for view change and the new view messages. Implementation. The implementation is as the same as we discussed in the algorithm. The replication library will maintain the service called a replication service, and what is the client duty? He just invokes the request, and what is the server duty? He may execute, he may check, or else he may make checkpoint, or else he may delete checkpoint. If at all there are any software problems, he just stops the process and he checks everything, and after checking it he just make sure that everything is correct, and then he will send back the reply to the client. And it is all done through the point-to-point communication using UDP, unidirectional protocol. Implementation: a byzantine fault-tolerant file system. Here we can see that in the client we have Handy benchmark. Handy benchmark is used to check the performance, and in the client we have also the relay replication library. It means it will store all the values of First, initially, client will send the request messages to all the replicas. Like we can see replica 0, replica 1 up to replica n. And after sending all the request messages, and then it undergoes three-phase protocol like prepare, and commit. And after undergoing all these phases, uh, it will decide which are faulty and which are non-faulty, and make sure that it will send all the response to the client after undergoes three-phase protocol, and it will send only the non-faulty processes, and it will store the all its values in the replication library, and in this way the algorithm works. Conclusion. Practical Byzantine fault tolerance is the initially repeated framework that works effectively in non-current framework like web, and it enhances execution of past calculations by more than a request of size. That means practical Byzantine fault tolerance is a framework that works very effectively in a non-concurrent like internet, and it has the all records of executions of that were taken in the past, and it has all the calculations of its own size. Like OM and SM algorithms are too slow to be used in the practical, and by this practical Byzantine fault tolerance is completed. And if you have any questions, you can directly put me in a course mail. I will try to solve those questions.